Good morning, everybody. I'm sorry about the technical difficulties. As you can tell, I don't do a lot of webinars. It's kind of a strange experience for me because I kind of like gauging what the audience is doing, and I don't know if there are 6 of you in the audience or a couple thousand, and I don't know if you're rolling your eyes back in your head or whether your eyes are completely closed. But on the other hand, I'm sitting in a hotel room in the DC area in my pajamas and bunny slippers, so it works both ways. So we're going to talk, when we were setting up this seminar, we thought it might be useful for those of you who aren't oil geeks, like many of us, to really provide a little context and background for what we're going to be talking about, and to try to explain why oil is difficult both to respond to and as well as to study in scientific investigations. So we're starting very basic, and I hope I'm not patronizing some of you, but here we go. So oil, petroleum, of course, is naturally occurring. You in the Gulf of Mexico know this better than almost anybody else in the country, and it's a mix of gaseous and liquid and solid materials. And maybe the most important thing to consider when we talk today is that it's a really complex mixture of thousands of different types of chemicals. And of course, we use that oil to make a lot of the stuff that we use in everyday life. So you're probably wondering if it's my cultural reference here. Some of you may be too young to even know what this is, but for those of us of a certain age, this conjures up fond memories. And the reason that I'm showing it is that this is, of course, is the Beverly Hillbillies, and Jed Clampett was known for going out shooting at some food, up from the ground come a bubbling crude, and that's very simplistic. It's just to remind people that oil is a natural material. It does come up in natural seeps, and in fact, the lower right here shows you a natural seep in the Ojai oil fields in California after the Northridge earthquake. It just started bubbling up from the ground. So we have these seeps all over, both on land and in the ocean. This is a slide from a National Academy of Sciences report that just shows the amount of oil that goes into American waters from natural seeps, and it's a pretty substantial amount. 63% of the oil that goes into our water comes from seeps. On the left-hand side, you see a seep off the coast of California. That's a picture I took off Santa Barbara, and there's a lot of oil that comes up onto the surface of the water. And the lower left, if you go up into the hills above Santa Barbara, even in the freshwater streams, you see oil seeping in there. So, the point is that oil is a natural product. Again, in California, this is platform Holly, one of the production platforms in the Santa Barbara Channel, and you see oil trailing off there from left to right, and that actually is not from the platform. It's from the seep that's located very close to platform Holly. So, we started off saying that oil is a complex mixture, and this is just a simple pie diagram that shows some of the compounds, the constituents that are in crude oil, and we'll see if this works. This is another way to show it. It's an animation that basically shows the same things, but for those of you who are a little bit more into chemistry, it shows you the chemical structure of some of the major constituents. So we see alkanes comprising about 30% of crude oil. Alkanes are simple straight-chain hydrocarbons. Naphthenes are also called cyclohexanes. They're about 50% of crude oil. Aromatics, we often talk, you'll be hearing, I think, a lot about aromatic hydrocarbons, 15%. These are compounds with benzene rings. You see the ring structures here. And then asphaltenes, about 5%. These are the real heavy compounds in crude oil, very complex. hard to define compounds, but it's really kind of the dregs of what's left in a barrel of oil after everything else is taken out. So here's a summary again of what's in a barrel of oil. And I think the takeaway is that it's a complex mixture. So just keep that in mind, and we basically have to take into account all the time what's in oil when we are responding to it or trying to study it. So those of you in the Gulf may be familiar with the terms on the left, from light sweet crude to heavy sour crude. And I won't get into what all of those things mean, but I think, again, the takeaway is that these different kinds of crudes have different mixes of the constituents in them. And the value of each crude is really dependent on what's in that oil. So the light sweet crudes are often highly valued because we get the things that we really like gasoline and other fuels like diesel and jet fuel. So we separate out the constituents, the different types of products in crude oil by refining it, and that's basically a distillation process. So the crude oil is heated up, and the different parts of the crude oil come off of that crude oil mixture at different temperatures. So at lower temperatures, you see the very light materials like gasoline and kerosene come off first, and then at very high temperatures, you get really what's left, things like asphalt and paraffins. This is pretty similar to, you know, what the old revenuers used to do, or the moonshiners do in some parts of the country and have done for a long time, distilling grain alcohol from mixtures. And in some parts of the world, there are even petroleum equivalents. This is a shot from Nigeria showing what's called an artisanal refinery operation. Folks hijack or steal oil in Nigeria and then refine it to get the high-value products out of it, which sounds a little quaint, but it's a very messy process. So Nigeria has a number of problems, but the holdings, the residual from doing this so-called artisanal refinery are pretty substantial in terms of environmental effects. All right, so I'm going to blast through basic oil properties, and these are things that we think about in response and how we deal with an oil spill. So that's what I'm emphasizing here, but you see three basic physical properties, density, pour point, and viscosity. And so density is, I think it's intuitive for many of us. It's basically, will it float on water or will it not? And there are two ways to think about density, and one is thinking about it in terms of specific gravity, and it's based on a comparison to pure water. So basically anything with a specific gravity or density less than 1 will float on fresh water. Anything greater than 1 will tend to sink. Now, in the oil business, we use something called API gravity, which is also based on the density of pure water, but it's a way to sort of standardize it to temperature and that sort of thing. The simplest way to think about it is that in an API density or gravity, anything greater than 10 is lighter than water. Anything less than 10 is denser than water. So, you know, this sounds pretty esoteric, like esoteric stuff, but when you get into oil spill response, we really need to think about density and specific gravity. And here's an example. A lot of the late news about so-called emerging risk oils have to do with Alberta bitumen coming from Canada. It's a very heavy product, and one of the primary questions in deciding whether to allow this stuff to go through in pipelines is whether it'll stink or not. And during testimony to the Canadian Energy Board, a lot of the industry folks pointed out that when they mix up the stuff that's transported in pipelines, it's basically like any other crude oil. So this is a guy that I've worked with since Exxon Valdez, Al Mackey, and he testified to the board that They simply cannot sink, and that's an important consideration. However, other reports, in fact, this one was from the Canadian government, said that, well, that's not necessarily the case. If you mix it with sediment in the water, it can sink. So specific gravity and density is an important consideration for response and for potential environmental effects. Again, pour point is another physical property. It's basically at what temperature will the stuff, the oil product, pour freely. So you see on the left a fluid material at a certain temperature, and on the right a less fluid one. It takes a higher temperature to get it to flow like the one on the left. An example from response, this is a shot from Spain, the Prestige spill, and it's an aerial photo of a bedrock shoreline. So you see heavy oiling there. This is from a tanker that went down off the coast of Spain. What was interesting was that it occurred in November and December, and the temperature, ambient temperature, was below the pour point of the oil. And so as it came ashore on this bedrock shoreline, it was pretty easy to clean up. You can see some Spanish soldiers simply shoveling the stuff up, and it kind of rolled up almost like a carpet. It was below the pour point, so it wasn't fluid, it didn't adhere. So viscosity is just a tendency of an oil to spread. We think about this a lot in terms of how it behaves both on the water and on the shoreline. Just some examples of how we measure viscosity. Lower numbers are more fluid and higher numbers are more like solids. So you kind of have some simple examples here, and you see some oils on the right-hand side. Okay, and you'll hear people talk about groups 1 through 5 oils, and these are kind of hard to define. I tried to get some numbers on how to define different groups, but I think maybe the most informative way to think about these things are simply the descriptions that are there on the left-hand side. So group 1 oils are very light oils. Group 5 are very heavy, and in fact, group 5 oils are sinkers. So that's probably the easiest, most intuitive way to think about groups 1 through 5. And the only reason I bring it up is that we have a rule of thumb about how these oils behave and how toxic they are. And what you're going to hear today is really some cutting-edge information on a new way to think about oil toxicity. So, you know, you look at this table of impacts to different kinds of aquatic organisms across groups 1 through 4 oils. And this is the way we thought about toxicity for a long time. But the folks who are going to be talking to you after I finally shut up are going to demonstrate some new ways to think about oil toxicity, and maybe they're going to show you that this paradigm that I have up here is not necessarily very good. Oil weathering, and I'm not going to spend any time on this, but the takeaway here is that when you put oil into the environment, it changes. It's like a chameleon. It's changing all the time, so it really affects how you deal with it in the environment and what the potential environmental effects are going to be. So again, I don't have much time to dwell on this slide, but going through those basic oil weathering mechanisms, there are just some highlights about what we think about when oil does spill. But in general, just keep in mind that the oil that spills initially is going to be very, very different from what the oil looks like after even a day or a week, or certainly after a month. So it's always changing, and it really changes how we think about it, both in terms of response and environmental impact. Finally, I'm just going to mention dispersants. I'm sure, you know, I know that dispersants are kind of on the radar for a lot of you. These are just some factoids about dispersants. They're another complex mix of materials, probably less complex than oil itself. And there's been a concerted effort to try to reduce toxicity over the years, but they're still really controversial. And you in the Gulf know this better than anybody. Just to show how dispersants work, on the left is some South Louisiana crude that's been mixed with seawater, shaken up for a little bit, And on the right, it's the same mix, but it was a little bit of Corexit 9500 in it. And you can see how much more oil is in the water on the right-hand side. And finally, this is just a list of what's in Corexit. And to, I guess, demonstrate that these are not completely exotic. They're not necessarily things you want to add willy-nilly to the environment, but they're commonly used in a lot of different consumer products. So something to keep in mind. I know we'll be talking about dispersants for a long, long time, and we in NOAA are going to be doing that in a structured way, trying to understand what we know and what we don't know. But in any event, I think that's all I've got. I just wanted to give you a quick overview, and so I hope that was not too quick. I hope you're still awake even after the morning coffee, and maybe we can talk a little bit more later on if you have any questions. Thanks.